we talked about continuity, and I said that this was kind of more of a more favorite section of mine, just because, well, it's a little bit more intuitive than the limits and all that stuff, okay? Continuity in general is you can draw the graph without picking up your pencil, right? That's the basic definition of continuity. But because this is a math class, it's not as simple, and we want to prove that something's continuous. So the main definition of continuity is that the limit has to exist. So we definitely can't have like a jump, right? Limit has to exist. We can't have a hole either. Oh gosh. Oh, no. We can't have a hole either. So the function has to be defined at the point that we want to prove continuity for. And even if the limit exists and the function is defined at that point, we still have to have them be equal for a continuity to happen, right? We can't have a hole with a dot somewhere else, okay? So that was our definition of continuity. The function is defined at the point, the limit exists, and if those two are whole numbers, they have to be equal, okay? Okay, we did a couple examples where we proved continuity at a point. So we worked through that. And then we started talking about, okay, maybe I don't want to prove that something's continuous at a point. I just want to know if it's continuous everywhere or where it's not continuous, right? So we talked about constant functions. Constant functions are continuous everywhere. The identity function, f of x equals x, is continuous everywhere. And polynomial functions in general are continuous everywhere. Okay, so whenever we see a polynomial, it's continuous. We also talked about rational functions. Rational functions are also continuous everywhere, except where the denominator equals 0. Okay, so where the denominator equals 0 is where we get a discontinuity. Now, we left off, I think Michael asked a really good question about, okay, when we have a rational function and we have a discontinuity, what is actually happening? Is it an asymptote? Is it a hole in the graph? What's going on? And the answer is it kind of depends. And we'll talk about two different situations where we might have a discontinuity, okay? So rational functions, polynomial over a polynomial, right? So definitely looking at these. Let's just talk about some of these functions, okay? Example number 4. We have a function, it's a rational function. We want to find where it's continuous. Where is this function not continuous, Michael?
1 and -1.
1 and -1, where the denominator equals 0. If you want a more systematic way to find that, you would take the denominator, set it equal to 0, solve for x, and we get plus or minus 1, right? So definitely continuous everywhere. Except x equals -1 and 1. Okay. Now I took it upon myself to put the graph of this function up here. And it looks like, well, the discontinuity actually happened because we have a vertical asymptote at -1 and at 1. Okay. So the discontinuity, it looks a little bit weird. It's not really, it doesn't seem like it could be a discontinuity, because if I drew this function, I would never pick up my pencil because I just go down forever, right? But because we jump up here to get to the vertical asymptote up top, this is also a discontinuity as well. Okay, so vertical asymptotes mean discontinuity as well. Okay, let's talk about a different function here. We've got x squared minus 25 over x minus 5. Where is this one discontinuous?
Nowhere. 5.
I hear nowhere, I hear 5. Let's talk about this. Well, the definition, or the thing that we talked about last class, said this is continuous everywhere except where the denominator equals 0, right? X minus 5 equals 0. So x equals 5 discontinuity, okay? Jude took a look at the graph and was like, nowhere. I graphed this function on Desmos, okay? Anyone want to tell me if there's something weird about this graph that you don't see?
There's a hole.
There's a hole, right? And okay, I know it looks like there's no hole. When you draw a function with a hole on a graphing calculator, Desmos, something like that, the hole actually doesn't show up, okay? It just doesn't graph the hole. I don't know why. But technically this function has a hole here. Okay, so it's got a hole there. So you can just kind of draw it on. Okay, so that's kind of the problem with graphing calculators, is they're not very accurate when it comes to like very minute details. All right, so we have a hole at x equals 5. It's continuous everywhere, except x equals 5. Okay, so the reason there's a hole instead of an asymptote here is, you don't have to know this, but if you factor the top, you'd get x minus 5 times x plus 5. They would cancel out and we're left with a straight line that looks like this. Okay, that's why there's a hole. Okay, so we looked at two rational functions. They both have discontinuities. One of them has a discontinuity because there's a vertical asymptote. The other one has a discontinuity because there's a hole. These are both discontinuities that can show up when we have rational expressions. Okay. Moving on. We actually looked at a couple different types of discontinuities now. There's names for them. You don't have to know the names, but let's just look at the different types. Okay. I think the first one that we talked about was the jump discontinuity. And it's called a jump discontinuity because, well, the function jumps from one thing to another, right? So piecewise functions where they don't, where there's a big jump, that's what we call a jump discontinuity. Okay. We also have our hole discontinuities, right? We have a hole where the function is not defined, and a hole where the function is defined, but it's defined somewhere else. We call these removable discontinuities because they're pretty easy to fix if you were to draw the function again, right? If I were to make the middle function continuous, I would just fill in the hole, right? So we call these removable discontinuities. We also saw the asymptotes as a discontinuity. We have infinite discontinuities, okay? This happens when we have an asymptote going on, okay? The last type of discontinuity I didn't talk about because I didn't put up the function is something called an oscillating discontinuity, okay? And this happens when we have a part of a function that just oscillates or just goes up and down like crazy between a certain interval, okay? So this function, the crazy part is what we call an oscillating part of the function. That's also a discontinuity just because it's kind of going crazy. You can't really zoom in on the function anywhere. We're not going to focus too much on that, but that is a discontinuity as well. Okay. All right. Next, I want to talk about some things, some applications of continuity. There's a very specific thing that continuity brings rise to, and we'll talk about this real quick. Okay. So let's take a look at this example. Ryan's my husband, by the way. He drove home this weekend. He actually didn't. He was at home. But he began at rest. Let's say the car was at a resting point in the beginning. And he drove 10 hours. His home's actually like 3 hours away. But after 10 hours, he was going 60 miles per hour. Okay. Let's think about this. Was he ever going 37 miles per hour? Yes. Why? Yeah, like he's got to accelerate up to 60 miles per hour. Okay. Let me show you what would happen if the answer was no. Okay. And the way I'm going to show this is by graphing his velocity. Okay. So let's say we have time as the x-axis. We've got v of t, which is the velocity function, right? So how fast he's going. And since Ryan started at rest, he started at 0, right? At time equals 0, he was going 0 miles per hour. Okay. The question said at 10 miles per hour, or sorry, at time equals 10 hours, he was going 60 miles per hour, right? So he was going this fast. Okay. And we know that 37 is a number between 0 and 60. So 37 miles per hour is probably here, right? Okay. So our question was, okay, was he ever going 37 miles per hour? Let me show you a situation where he wouldn't be going 37 miles per hour. Okay. Let's say, I don't know, he sped up, he was driving, he got up to here, and then suddenly he started going 50 miles per hour. Okay. Is that a realistic situation? No, right? Cars don't normally do that. Okay. The reason why he was going 37 miles per hour then is because his velocity is a continuous function, right? So a car's velocity is continuous, usually. Okay, and continuous functions don't have jumps like this, okay? So the answer is yes, he was going 37 miles per hour. And the reasoning is because his velocity is continuous, okay? Because velocity is continuous. Okay, what I just did is I applied something called the intermediate value theorem. Okay, I don't know, some of you might have heard this before. Okay, and let's just talk about what this actually says. Okay. This is a theorem that is very, very important in calculus. If you're a math major, you're probably going to hear this a lot in the future. But it only applies for continuous functions. Okay, so the big thing about this theorem is it only applies if a function is continuous. Okay, and it's continuous on an interval. Okay, so a, b. Let me draw a picture as I explain this. Okay, so we have a graph of a function. Could have made these lines a little bit better. Okay, and our function is continuous between a and b. Okay, so between these points, our function is continuous. Okay. Okay, so since our function is on a and b, well, our function has to have a value between this, right? So our function has to, let me draw it a little bit better. Let's say our function goes here, goes down, and then goes here. That's a continuous function. Okay. F of a is its value at a. So this is f of a. Okay. F of b is the function's value at b. So this is f of b. Okay. Now the intermediate value says, let n be any number between f of a and f of b. Okay, so n is something in the middle. Okay. What this theorem says is if we have this condition and it's all set up, the function's continuous, n is between f of b and f of a, there exists at least one value c between a and b, so an x value, such that f of c equals n. Okay, so what this is saying is, okay, between a and b, there's got to be something, some x value in between a and b, such that n has a value. And it looks like there is one. Okay, so it looks like c is here. Okay, this always happens when we have a continuous function. Okay, now one thing is this theorem isn't saying that the function has to be between f of a and f of b, between a and b. The function can go down, right? This function went below f of a and f of b, but there is one value where our function takes the value in. Okay, now I know that's really abstract, so let's just do a couple intermediate value theorem questions and it might clear things up. Okay, so when we do intermediate value theorems, which is basically checking to see if our function takes on a value n for something between a and b, okay, we have to do a couple things. Okay, the first thing we want to do, we want to state that f of x is continuous. Okay, we have to explain why it's continuous if it's not stated already. Okay, we're also going to find f of a and f of b, and then we're going to say by the intermediate value theorem there's a number. I don't know. Instead of saying part 3, let's just say that the claim is true. I have no idea what I meant when I wrote that third part. Okay. All right, let's do an example. So we have this function, okay? We have x squared plus x plus 1. It's saying, how do I know that my function equals 7 for some x value in between -2 and 3? Okay, so if you want a picture of this, okay, I have my function. I don't know what it looks like. I got -2 here. I've got 3 here. Okay, maybe I know that 7's here. Okay, how do I know that between -2 and 3, my function takes on the y value 7. Okay, this is what this question is asking. Okay, so intermediate value theorem, it only talks about continuous functions. So we might as well state that f is continuous, right? Okay, how do I know that f is continuous? It didn't say it in the question.
Because it's a parabola.
Parabola, polynomials are continuous, right? So I have to say because it is a polynomial. Okay. Next, it might be a good idea to find f of a and f of b, right? F of a and f of b. A here, what is a? -2, the leftmost part of our interval. Okay, so f of 2 is, let's see, we got -2 squared plus -2 plus 1. I'm really bad at mental math, but let me, is it 3? Okay, I think you're right. I wrote that down on my paper. Okay, and then f of b is 3. So 3 squared plus 3 plus 1, I got 13. Okay, so essentially what this is saying is we have our function, f of 2 is 3, okay, f of 3 is 13. Our function's continuous, so do we hit 7 in between -2 and 3? Yes, right? And the way that we explain this is we don't need to draw the function. Of course, you can kind of sketch it out if you want, but all we have to say is by the intermediate value theorem, f of x has to be 7 somewhere, or for some x between -2 and 3. Okay, that's how we kind of explain our answer. Okay, now most questions with intermediate value theorem aren't going to ask us this, but why don't we just find the value of c? Okay, any ideas on how I would find the c value? Where does my, oh, I graphed it, that's true. There's actually an algebraic way to do it, Sam.
Put 7 as like the result.
Yeah, right, it says f of x.
That's basically the 7.
Yeah, no, you're good, I got what you meant. It says f of x equals 7, so instead of f of x, let's write what it actually is. X squared plus x plus 1 equals 7. Okay, well, now we can figure that one out. If I subtract 7 from both sides, I'm going to get x squared plus x plus, oh, -6, right? Equals 0. How do I factor this guy? What are the factors? 3 and -2, right? They multiply to 6, add to 1. So we have x plus 3, x minus 2 is 0. That gives me x equals -3 and +2. Okay. So what is c? Is it both of them? It's 2, right? Because c has to be between -2 and 3. The only value between those two numbers is 2. Okay, so c is actually 2. So our function actually passes through 7 at 2. Okay, now in a lot of these IVT questions, we actually can't find the value of c because it's going to give us a crazy function. Okay, it's going to give us like x to the 17th or something like that. Really can't solve that, but in this example, it's simple enough that we can find the value of c. All right, I'm going to talk about example 8. I promise I'll let you work on it on your own, but let me just explain how this is a little bit different than example number 7. Okay, first of all, our equation is a little bit different, right? We have x to the 5th going on, which is a little bit weirder. Okay, and we have the interval 0 and 2. Okay, this one's asking us, is there a solution to the equation x to the 5th minus 2x cubed minus 2 equals 0? How is this the IVT question?
The equaling 0 is like the equaling 7.
Yeah, right. equals 0 is kind of like equals 7 in the last example. It's asking us, and for this example, why don't I just make a function f equal to x to the 5th minus 2x cubed minus 2, okay? If I want to phrase this question kind of like the example 7, this is asking us, how do I know that f of x equals 0 between 0 and 2? Okay, so same question as example 7, it's just worded a little bit different. It's asking us, how do I know that the function equals 0 between these 2 points? Okay. I'll give you a few minutes to work on this. Just talking, you know what, let's go back to example 7 real quick. I probably should have put a better explanation as to why the IVT works here. The reason the IVT works here is because 3 is less than or equal to 7, which is less than or equal to 13, okay? I would recommend writing that. Okay. Now I'll let you work on example 8. Example number 8. Do you kind of want to talk about your process here?
So first step, just confirming that it is continuous. It's a polynomial, so yeah. The second step, just finding f of a and f of b, and then setting up that 0 lies between f of a and f of b in the third step.
Perfect. This is all you need to write. But oh yeah.
Why are you asking about 0 though? Isn't y equals 0?
Yeah, and why we're asking if y equals 0, right? And these two are y values. So since this y value 0 lies between -2 and 14, we know that there's an x value. Does that make sense? Good. With these questions, you need to write that the function is continuous and you need to explain why. Okay, so definitely make sure you do that. You need to find f of a and f of b. Okay, and you need to write some sort of semblance that the IVT is working. I would recommend writing like, okay, I know that 0 is between these two numbers, then we're good. Okay. Any questions on example number 8?